Good afternoon. My name is David Levy. I'm a product manager with Microchip. We're going to go ahead and talk a little bit about the future of mission-critical edge compute. And we're going to talk about how RISC-V is helping advance it. So in our agenda today, we're going to cover a few items. One is, what is mission-critical intelligent edge? What are some of the target markets and key usages? What are some of the benefits of the RISC-V technology? We're going to tell you a little bit about our new product, PIC64HX, which incorporates the RISC-V advantages and technologies we'll talk about. And then we'll have conclusion and call to actions. So let's start off with a definition of what do I consider mission critical and how does it relate to computing? So mission critical in simple terms is a way to describe work activities that need to come to a successful outcome. If for some reason the parameters aren't set correct, your mission will fail. And so there are different markets. They all have where failure for a process to complete would result in a negative outcome. In our terms, we're going to talk about space, aerospace and defense a little bit, and industrial products. And we're going to talk about what's important to those markets. And what you can see is those markets are outlined on the left. On the right are some of the computing attributes, which, although these markets are solving different problems, they still have to have some commonalities, and here are several of the commonalities. They need the ability to have high performance, and when we're talking about high performance, we're talking about throughput on the system. They need to have real-time enablement, so they not only need information, they need it at a certain time, and they need to transact in a certain amount of time. They may need virtualization because you might be trying to work on several different challenges at the same time. And virtualization allows you to divvy up the hardware and keep track of the resources and do the problem solving. We have partitioning and isolation, which helps with that. What you've heard a lot of today is AI and ML, and how do you go about moving more data quickly? And it's through vector extensions and vector processing. It's multiplication math, so you can move a lot of data concurrent rather than trying to move one piece at a time and just looping it over and over again. You might need cores working together. So we normally refer to that as symmetric. They're given an equal amount of data, and they're all working together on that. You might need asymmetric, where you're having to break it up and have different cores focus on different problems. Fault tolerance is something that we run into in a lot of these applications where you need the product to perform, and so it has to be available and ready to perform. So it's got to have built-in backup and redundancies. Radiation performance usually comes into play in space. It has to deal with bit flipping and making sure that the computing is staying on track. We have connectivity and security. They've talked about that extensively throughout this seminar. If you're moving a lot of data, you need to have not only bandwidth to do so, you need to make sure that it's going to the right places and it's not being compromised in the process of movement. Time and space partitioning operations is used to make sure, do you have a clear hardware path, and are the transactions being isolated and properly routed through there? And then in a lot of cases, if you're running cores, especially in asymmetric mode, you might need multiple OSs on the same system at the same time. And so these are areas that we've outlined. There are commonalities across all of these markets. So what we're going to do is talk a little bit about what drives these markets, what sort of applications, and then you can see specific to each market which ones on that prior slide are relevant to the market, as well as how is RISC-V playing to advance it. So if you look at the space market, the space market is on a trajectory to grow 7% CAGR between now and 2035. Half of that is coming from directly putting products up into space, and the other half is actually the operations in space. And you can see the source of this was from the World Economic Forum. So they're tracking growth in different markets. The applications we see it in, we've talked a little bit about. It could be either in space itself, or it can be getting up to space through application like a launcher. If you look at the compute requirements, these are the ones that were outlined on the first page that carry over to this market. And what you'll see is traditional space processors, normally when you're designing for space, you're going to design a product, and then you're going to want it to operate up to, could be 15, 20 years. It depends on how far out a product is going. And so traditionally, you're focused on radiation coverage, and you have to make compromises. And so that comes in the terms of performance. So with the new products and the new challenges they're trying to solve in space, you're going to need to add the ability for recognition of objects in AI and doing autonomous transactions there, as well as you're going to have to be able to, with those high-definition sensors, not only capture the data, you've got to move it to computing where it can calculate, what do I do with this information? We're going to need high-performance computing if you're collecting a lot of data, much more than single-core processors, which traditional space is utilized. We're going to need redundancies to make sure that the system stays up and running. And now is a generational opportunity to go into space. RISC-V offers some good economic growth as well as new ISA instructions, so you're not worried about dealing with all the legacy that has existed before. You're trying to set a new baseline. If you look at aviation, aviation has some parallels to space, minus some of the ruggedization. And if you look at market opportunity, we follow lots of the commercial airline providers. So Airbus, for example, is a good example. They're showing us they expect to have intensive growth over the next decade and a half. And it's going to grow 2x. So today they have aging fleets out there. And those fleets need to be replaced, and they also need to be modernized. Some of the modernization they're going to work on is, it's called SWAP. It's size, weight, performance. They're trying to make things lighter so you can either gain more fuel efficiency out of an aircraft or possibly even move to electric propulsion, items of that nature. And when you're looking at that, you have to bring in a very clean solution because there's human safety involved. And so when you're looking at these areas where RISC-V has great opportunities to make inroads is the fact that an airline needs dissimilar solutions. So they will probably use an ARM architecture, and at the same time they need a parallel processing running, also computing solutions, but it has to be a different architecture. And when you do that, the solution that's been in place for a long time is PowerPC, and now RISC-V has a great opportunity to come in and supplant that. Next generation aircraft we talked about are going to need better performance. They're going to need the ruggedness. They're going to need the lightweight aspects. We've already talked about fault tolerance through the fact they're running two different computer systems concurrently. And so the growth of the ecosystem here is what's going to be critical for RISC-V to get a lot of traction. If you look at industrial edge is probably what most of us are touched with in our daily lives on terrestrial uses. There's embedded microprocessors, which can go anything from a soda machine or some of the dispensers you've seen in the hallways in this building to automotive networks and robots actually assembling cars. And then the other area that you've seen a lot of explosive growth on over the last few years is application and multimedia processors. As folks are starting to incorporate cameras, they're capturing a lot of visual data. And that visual data needs parallel processing in order to get great performance. So RISC-V is working on bringing improvements to all these areas. It's working on AI and autonomy through visual capture and how it deals with it with vector extensions. It's dealing with moving the traffic around the system using high-speed Ethernet and using time-sensitive networking, the protocols, so that way it can prioritize which messages get through the system and when. And there's a whole new cycle of investment going on in industrial networks. There's lots of aging factories. They need wiring upgrades. Wiring costs a lot of money and takes up space. And so these networks are trying to utilize IT and OT information on the same cable. And in order to do that, you have to ensure that the traffic stays separate. And so RISC-V is helping us introduce some solutions in that space. There needs to be safety for human involvement in these processes, and there also needs to be redundancy. So if a system needs to be up and running, it's available and up and running. Where you're going to see in factories security concerns is post-quantum computing. You don't want one of the robots in an assembly line, for example, to get compromised and it starts running out of synchronization with the others. That creates quality issues in product assembly. So that's where you'll see some examples in industrial. We talked a little bit about this morning. We saw it in Patrick's overview this morning. We've also seen it in some other products where we talked about there's a need for computing in multiple ways. And with RISC-V, it enables flexibility in how you assign that computing. So instead of buying different processors to address each one of these types of computing, you can buy one processor and assign how would you like it to be operating. Do you want it gang tackling and working together in a symmetric process? Or do you want to break up the resources and solve multiple problems concurrently? So RISC has that. RISC-V also is enabling hypervisors, so you can take the hardware and divvy it up that way and keep the isolation. So when transactions need to occur, they do occur. There's also safety factors which get built in, and that's this bottom area we're talking about. It's called dual core lockstep. That's where you could have two processors running in parallel. You have one actually running the workload, the other one's ghosting it, and it compares the results. As long as the results are the same, you're good to go. If the results are different, your software stack has to tell you, how do you want to resolve this difference? You guys probably see that every day in your vehicles on the road. They also are using that in other types of equipment, like defensive equipment and even planes. So isolation is going to be one of the keys to how you successfully deploy RISC-V in the future. And there's hardware and software isolation available. The operating systems, as you guys can see, reading across the top, we support Linux, we support real-time operating systems, as well as hypervisors. And with those, that's how you assign the access to the hardware. And so there's multiple hardware solutions that you can use. One's privilege levels. You probably have seen the traditional circles in x86, where the closer you are to the center, that's the least amount of access you get. As you move out, then your OSs and your apps start to gain access. And so RISC-V has that same capability with privilege levels. There's also I/O assignment through MMU. And with that, you can control where the resources are getting directed on your hardware system. WorldGuard is it's an isolation mechanism which can break up your hardware resources into as many as 32 worlds. And what gets assigned to the world stays in the world. What isn't assigned to that world gets rejected should it try to access it. It's a great way to ensure your space and time partitioning and ensure your transactions are getting through when they're needed and cleanly. The other sort of technology solution they have is physical memory map and physical memory protection. And in here what it does is it prevents anti-tamper, and it also prevents items like buffer attacks. So your memory is not getting accessed by areas it should not be. This is a good example of WorldGuard isolation. What it's showing you is you have different worlds, and depending on how you're breaking up those hardware resources and assigning them, that's what transactions will get through. And so when you're working with WorldGuard, you can isolate by core, cache, memory. You can isolate by your I/O NOCs. So it gives you really good capability to control what information's getting throughout there. And it gives you the high reliability of, we said it's isolated, you can prove it's isolated. That's what it's for. The topic that got a lot of coverage today was AI/ML. And that's, there's going to be a lot of problems where we need to do automation. It could be a mundane task, so it's really repetitive. Or it could be something where it's sifting through a lot of information and you need it to boil down to what was important and what do I need to make a decision on quickly. And that's really where it will become important. If you use the vector extensions, what we've seen is instead of taking an instruction and looping it through a single core many, many times, you could run them in parallel. You guys have seen this a lot in GPUs and that technology. You can get up to 144% performance improvement versus just doing a loop instruction. The benefits of this are with RISC-V, the vector extensions, they're modifiable. And you don't have to define it before runtime. During the running, it can actually take different sizes and apportion them. That's an advantage to this technology. There's small programming models. We don't have a lot of legacy information in there. And so they're fast, and they're also optimized. So this will help you. The other area where it will help you is you're going to have the ability to use open source, the tools, and the software stacks to tune your systems for a RISC-V platform. So it uses the same tools that other ISA providers have. So they're common and they're available, and you're just optimizing it for the ISA called RISC-V. So the reason we've talked to you about what are the advantages of RISC-V and some of the technologies and advancements it's bringing is because Microchip's launched a new PIC64 product line. It's the latest addition to our MPUs. So Microchip has traditionally had 8-bit and 16-bit and even 32-bit controllers. Now we cover anywhere from 8-bit to 64-bit. What we're trying to do is make sure we have performance to meet many application needs. Within PIC64, what we're doing is we're allowing you to port some of the tools that have been useful to the 64-bit using MPLab. And you have now a very broad catalog if you're trying to do problem solving out in the market. PIC64HX itself.
Yeah, I gotta cut you off, sorry.
Okay. All right. We're good.